the theoretical framework with endogenous growth. So far we have been talking about growth in an exogenous sense. Exogenous meaning that the technological innovation that we were talking about, uh, that technological innovation is exogenous in nature, right? So you can think of it as an outside shock or like an exogenous shock. So in the last lecture, what we did was we looked into solo swan model with technological progress, meaning that labor intensive technology was incorporated in the solo swan model. And once we incorporated labor augmenting technological progress into the solo swan model, this is what we got. We were able to reproduce the the result that there is growth of per capita variables in the long run. So long run growth was possible. It was possible to reproduce long run growth, that is growth of per capita variables, with the help of exogenous technological shocks, right? So when the growth that we are talking about, that growth, keep in mind that is not growth of growth per capita, right? So per capita is growth per capita of any variable. Let's say output is basically total output y divided by total labor, right? So per capita basically means per unit of labor. So here, when we are talking about growth, we are not talking about growth of per capita variable. So, for example, output growth is not growth of per capita output, right? Per capita output is Y by capital L. But the growth that we are talking, we were able to reproduce in the long run. So in the long run, there is constant growth, but this constant growth happens to output per unit of effective labor, right? So effective labor is basically labor times technology. So effective labor basically means how efficient this labor is, right? So that is the idea. So this the graph that you see on the screen, that is basically it's this is this replicates the steady state of a solo swan model with technological progress. It's similar to our the solo swan model that we are familiar with, that we had been talking about in the past few lectures. But the only difference here is that, see, first difference is that we have incorporated technology, right? And also, after incorporating technology, the variables that we are looking into, those are variables in variables expressed per unit of efficient labor, right? So basically, if you look into this figure, what you would find is uh, the growth rate of capital per effective worker, that is K hat. So capital per effective worker is represented by K hat. That is basically K by LT instead of per unit capital, per capita capital. Per capita capital is just K by L. So here capital per effective worker is K divided by LT, and that is given by the vertical distance between the SF K hat by K hat curve and the effective depreciation line. So this is the effective depreciation line, right? So here, as you see here, the effective depreciation, basically it's the sum total of growth rate of technology, then growth rate of population, and finally the depreciation rate of capital. So economy is at a steady state when k hat, small k hat, is a constant, right? So basically, see here in the steady state, what happens is all these variables grow at a constant rate x. Earlier, without incorporation of technology, what happened was this growth rate was equal to 0 in the long run. Here, this growth rate is positive. We are actually able to reproduce positive growth rate in the long run, right? So positive constant growth rate. So T technology, if it grows at a constant rate x, then the steady state growth rate of output would be the same, and capital per person also would be the same. It would be equal to x, right? So see the point of intersection of the SF k hat by k hat schedule and x plus n plus delta schedule, that represents the steady state level of capital. And keep in mind, this steady state level of capital, capital is basically capital per unit of effective labor. That is, at the steady state, this is basically a constant. K hat is a constant, right? So at the steady state, what's happening is this capital is growing at a constant rate, right? So the steady state growth rate of capital per person is actually a constant, that is equal to x. So just to recapitulate, what happens here is that in this framework, all the variables with hats are constant at the steady state. So the per capita variables, which is per capita, so capital K star hat is a constant, right? So Y star hat is a constant, C star hat is a constant. So therefore, per capita variables, that is small k, small y, small c, that is which basically represents total capital by total labor, these now grow in the steady state at the exogenous rate of technological progress, that is x, right? So what does that mean? Basically, all the per capita variables, per capita capital, per capita output, per capita consumption, that is small k, small y, small c, these now grow at the steady state rate of exogenous rate of technological progress, that is a constant, that is fixed at x. Okay, so the level variables, that is capital Y, capital K, capital C, is total output, total capital, total consumption. These grow accordingly at the steady state at the rate n plus x, right? Because these are basically, it's k, small k times n, right? So if you do, capital K is equal to small k times labor. So, you do the hat calculus and you would find that the rate of growth of capital K would be equal to the rate of growth of labor, that is n, plus the rate of growth of capital, that is so capital per unit of labor, small k, that is x. So the level variables, capital K, capital Y, capital C, these grow in the steady state at the rate n plus x, right? So there, the growth rate of the variables in level is basically equal to the sum of population growth and technological change. So you should notice that, as in the prior analysis, the analysis that basically neglected technological progress, shifts to the saving rate or the level of the production function affect long run levels of K star hat, right? So any shift in the production function is going to affect the point of intersection, right? The point of intersection between the effective depreciation schedule and the SF K hat by K hat schedule. So as a result, what would happen is the I mean, if we consider any any shifts in the saving rate, or any changes in the saving rate, or any changes in the level of production function, or any changes for that matter to any of the parameters here, x, n, or delta, then basically what would happen is the long run levels of capital output consumption per unit of effective labor, those would change accordingly. However, the steady state growth rates would not change, right? So only the point of intersection determines the levels. This is very important to understand, that this equilibrium is determining the level of capital per unit of effective labor. It is not in any way determining the growth in this variable, right? So any parametric change would accordingly influence the level of these variables, that is capital per unit of efficient labor, output per unit of efficient labor, consumption per unit of efficient labor, etc. Now, these kind of disturbances basically influence growth rates during the transition from an initial position, which is, suppose capital starts from this particular level. Suppose, this level is represented by k hat naught. Then, suppose the economy is moving from an initial position here to k star hat. So during this movement, during this transition period, any kind of disturbances, any kind of changes in parametric changes or changes in technology would influence growth rates. So growth rates are going to be influenced during the transition from an initial position. And also what would happen is, while growth rates are going to be altered, you have to keep in mind that the economy hasn't yet reached the steady state. So once the economy reaches the long run, once it reaches the steady state, any kind of shifts in technology, any kinds of shifts in in any of these parameters, changes in any of these parameters, is not going to make further changes to growth, because the constant growth rate has already been reached. What it would do rather is it would only make changes to the level of the variables per unit of efficient labor, right? So as in the previous framework, any kind of parametric changes or any kind of slight disturbances would influence growth rates during the transition from an initial position to the steady state value, in this case, k star hat. So if we are looking into a transition of the economy from initial position, let's say k hat naught, from there to k hat star, then during this this transition phase, if any kind of changes in technology happens, then that would definitely affect the growth rate during the transition phase. But once the steady state has been reached, there won't be any further changes to the growth rate. Growth rate would be constant. Okay, so this is you can do you can play around with the parameters and you can see for yourself. What can be done is, the Solo-Swan model can be extended with different kinds of capital. So what you can do is you can make a distinction between physical capital and human capital, and you can see how the production function would change accordingly and how the results might change. So that is something that we can look into later on, but for the time being, we should get a move on with what we are doing here, which is to understand the different theoretical frameworks when it comes to exploring growth theory. So far, whatever we have been trying to understand, everything is in terms of exogenous growth. not endogenous growth, right? So one crucial underlying assumption of exogenous growth is that the neoclassical growth model, so to say, is that the technology that we are working with, that actually that kind of technology has diminishing returns to scale, and because of diminishing returns to scale, you know as as time progresses, the capital capital stock would get exhausted, and hence a point would come, we would reach a time point when there would be no growth at all. So the growth of per capita output would reach zero, right? So we would not be able to reproduce a constant positive growth rate in the long run if we are dealing with diminishing returns to scale technology. So perhaps it would be a better, it would be better from a practical point of view to use constant returns to scale technology instead of diminishing returns to scale technology. So this is another aspect that we would be looking into. So now, another way of getting rid of this problem, problem of capital stock getting exhausted and growth process coming to a halt. So another way to do it is to endogenize technology, right? So actually, in the mid 80s, there was a lot of theoretical dissatisfaction with the neoclassical theory. So during that time, economists came up with new sort of theories and new models. So like it became increasingly clear that the standard neoclassical growth model was theoretically unsatisfactory as a tool to explore the determinants of long run growth. So what we have noticed is that the model without technological progress predicts that the economy will eventually converge to a steady state with zero per capita growth. This is the main issue, right? So if that happens, then the growth cannot be made sustainable, right? So we have to think of a different model, right? So the fundamental reason is the diminishing returns to capital. So one way out of this problem was to sort of broaden the concept of capital, notably to include human components, and then assume that diminishing returns did not apply to this broader class of capital. So we will talk about this approach later on. There's another view. This particular view was that technological progress in the form of generation of new ideas was the only way that an economy could sort of escape from diminishing returns in the long run, right? So basically, it became a priority to go beyond the treatment of technological progress as exogenous and instead to explain this progress within the growth model itself, right? So since there was a quest to sort of explain the technological progress within the model. So hence, these sort of models were called endogenous growth models, because it was an effort to endogenize the technological progress, right? So that is the thing. So it became a priority to go beyond the treatment of technological progress as exogenous. There were limitations to doing that. So people were trying to explain the technological progress from within the model itself. However, endogenous approaches to technological change encountered certain basic problems within the neoclassical model itself. The essential reason is the non-rival nature of ideas that underlie technology. So I'll talk a little about this problem. So see, this is the issue. So keep in mind that a key characteristic of the state of technology, T, is that it is a non-rival input to the production process. So technology is very much non-rival. So if we are to replicate technology, that can give rise to certain problems. So the replication argument that we used before to justify the assumption of CRS, constant returns to scale, basically suggests that the correct measure of scale is the two rival inputs, that is capital and labor. Hence, the concept of constant returns to scale that we used is basically homogeneity of degree 1. This is very much homogeneity of degree 1, right? So homogeneity of degree 1 in capital and labor, these two inputs, basically, not in T. So T is remaining constant, right? So you need not bother about T for the time being, right? So all this is because we need to make these clarifications right at the outset because of the non-rival nature of ideas that underlie technology. So when we are talking about constant returns to scale or homogeneity of degree 1 in either of the two inputs of capital and labor, then according to this is how it happens. We talked about it before. So if either of these inputs K and L get multiplied by lambda, then the total output would be would change like this, lambda times the previous level of output. So according to Euler's theorem, a function that is homogeneous of degree 1 can be decomposed in the following way, in this particular way. So marginal productivity of capital times capital plus marginal productivity of labor times labor. So the entire production function can be split up, it can be expanded in this form, right? So in our analysis up to this point, we have been assuming that the same technology T is it's freely available to all firms, right? So this availability is technically feasible because T is non-rival. However, it may be the case that T is at least partly excludable. For example, because of, let's say, patent protection, secrecy, and maybe experience might allow some producers to have access to technologies that are superior to those available to others. So for the moment, we maintain the assumption that technology is non-excludable. So basically, because of this assumption, all producers have access to the same technology, right? So this assumption also means that a technological advance is immediately available to all producers, right? So it's not the case that some people have access to technology, some people might not, or maybe technology that is used by some firms is superior to some others. We are relaxing that assumption for the time being. So what we are assuming is technology is non-excludable and all producers have the same access, basically. So this is the thing. So because of this, technological advance is immediately available to all producers. Now, see, from our sort of previous analysis that perfectly competitive firms that take the input prices capital R and W as given, these firms end up equating the marginal products to the respective input prices. That is, Fk is equal to capital R and Fl is equal to W. So it follows from this previous equation, this equation 41. It follows that the factor payments exhaust the output, right? Sort of exhausts the output. So after you pay for
Excuse me, sir. Sir, you're muted, sir.
okay, yeah, I have unmuted myself. All right, so suppose you know I hope I have not been muted for a long time, because see, what happens is sometimes it gets muted automatically, so I have no control over it. So if it happens, if I get muted accidentally, please point it out so that I can unmute myself. Okay, so what we were talking about is, let us suppose that a firm has the option to pay a fixed cost, in this case, a small cost kappa, to improve the technology from this level T to T prime. Okay. Now, since the new technology would be freely available to all other producers, we know that the equilibrium values of the input prices, that is R and W, would again, uh, it would lead to a zero flow of profit from each firm. Therefore, the firm that paid the fixed cost kappa will end up losing money, because the fixed cost would not be recouped by the positive profits at any future dates, right? So basically what follows is that in the competitive neoclassical model, you cannot sustain purposeful investment in technological change if technology is non-excludable as well as non-rival, right? So technology, if we are dealing with non-excludable technology, you you know this particular model, that is neoclassical model, cannot sustain investment in technological change over a prolonged period of time. That cannot be sustained, right? So the obvious next step is to allow the technology to be at least partly excludable. So to bring out the problems with this extension, we can consider the polar case of, let's say, full excludability. That is, where each firm's technology is completely private. Okay, that also happens actually. Um, Assume, however, that there are infinitely many ways in which firms can improve knowledge from T to T prime by paying the fixed cost, this fixed cost kappa, like in other words, there is free entry into the business of creating formulas, let's say. So if we suppose that all firms begin with this level of technology, T, would an individual firm then have the incentive to pay this amount, to pay kappa, and to improve the technology from T to T prime? Is, would it be feasible for one particular firm or for an individual firm to do that, to pay the price and improve its technology? Would an individual firm have the incentive to do that? So, in fact, the incentive appears to be quite large, right? So, at the existing input prices R and W, a neoclassical firm, a firm operating with the neoclassical model with a superior technology, would make a pure profit on each unit produced. Now, because of the assumed constant returns to scale, the firm would be motivated to hire all the capital and labor available in the economy, right? Just by hiring more and more capital and labor, more and more inputs, it can, theoretically, it can go on increasing its profits, right? So in this case, the firm would have lots of monopoly power and would likely no longer act as a perfect competitor in the goods and factor markets. So the assumptions of the competitive model would basically break down in that case, right? So a more basic problem with this particular result is that other firms would have predicted the same profit opportunity, right? So there are, arbitrage opportunities would set in, right? And, basically, since other firms would have perceived the same profit opportunity and would also have, paid the cost kappa to acquire a better technology, T prime. Because of that, other firms would be interested to do the same, right? However, when many firms improve their technology by the same amount, the competition pushes up the factor prices. This is very crucial for us to understand that whenever there's competition, the prices would go up. In this case, the factor prices would definitely increase. So it would no longer remain at the same level R and W, right? So, if that happens, then the flow of profit is again back to zero, right? So in this case, none of the firms can cover their fixed cost kappa. Just as in the model with, with technology, where technology was non-excludable. Here also, none of the firms would be able to cover for the fixed cost. Therefore, it is not an equilibrium for technological advance to occur. I mean, if all innovators are making losses, then it won't be feasible for an equilibrium to occur. And it is also not an equilibrium for this technological advance not to occur, because if technological advance does not occur, basically what that means is potential profit to a single innovator is like infinitely large. So that cannot be an equilibrium also. So these conceptual differences, basically these differences motivated researchers to introduce some aspects of imperfect competition in order to construct satisfactory models in which the level of technology can be advanced by purposeful activities such as R&D expenditures. So this potential for endogenous technological progress and hence endogenous growth may allow an escape from the diminishing returns and the aggregate level of capital going down. So basically, all this is in a quest to escape from our diminishing returns to scale, that particular feature of the technology, right? So basically we want to escape from the diminishing returns at the aggregate level. So the potential for endogenous, endogenous technological progress or endogenous growth may allow us to do so, right? So models of this type were basically pioneered by Romer, 1990, and Akian and Howitt in 1992. So these were the pioneering works. So if time permits, we are going to look into the basic theoretical framework in those models. But for the time being, let's stick to the basic theoretical frameworks. Just try to understand what's going on, and then let's try to understand the basic intuition behind these models. Rather than getting bogged down too much into the nuances of the mathematics and so on. So for now, what we would do is we would deal only with models in which technology is either fixed or varying in an exogenous manner. Okay, so the first model that we are going to study in this context is the AK model, right? So this is a very basic, classical um, model. It's the benchmark of any endogenous growth literature. So you cannot study endogenous growth literature without studying the AK model. So this is once again a very simple sort of framework, as you can see, for the technology to be exactly equal to A times K, as in output is produced only through capital, right? So it's A being the total factor productivity, K being the total level of capital. So A times K represents the output that you are producing. So a key property of this class of endogenous growth models is the absence of diminishing returns to capital. So one thing is obvious, the purpose for using this, rather simplistic kind of production function is because we want to get rid of diminishing returns to scale, right? We want to get rid of diminishing returns to capital. So the simplest version of a production function without diminishing returns is definitely the AK function, right? So as you see here, A is a positive constant, right? A is definitely a positive constant that reflects the level of technology. Uh, Now, the global absence of diminishing returns may seem a bit unrealistic because, in reality, there is diminishing returns to a certain extent. Diminishing returns to a certain extent actually exists in reality. But, the idea becomes more plausible if we think of capital in a broad sense to include human capital, right? So, long before this kind of literature emerged, Knight, that was in the 1940s, I think, stressed the idea that diminishing returns might not apply to a broad concept of capital. So the thing is, when we are, even this type of technology, the idea had been there for quite some time, right? So, the first economist actually to use a production function of the AK type was von Neumann, and he did it. I mean, he was a contemporary of Keynes, so he developed this idea sometime in the 30s, late 30s or early 40s. So the thing is that a global absence of diminishing returns, this particular idea, this feature, it becomes more plausible if capital is thought of in a broader sense. That is, if we think of a broad capital in a as in if we incorporate a broad category, different categories of capital to K. So K might be when we are talking about K, we are talking about capital in a very general sense, and definitely K can be split up into different categories, and human capital may very well be one of them, So there will be various categories of total capital, and definitely we can include human capital, right? So if we do that, then definitely the global absence of diminishing returns, it would not seem that unrealistic after all. So output per capita, if we are using this kind of a technology, then output per capita, see, it becomes y, capital Y is equal to A times K. So output per capita is capital Y by L. That should be equal to capital A times capital K by L. So small y should be equal to capital A times small k, right? So just to shift the model in per capita terms, this would be the technology we'll be dealing with. So this basically implies that the average and marginal products of capital are fixed at A. The average product of capital is A, and so is the marginal product, and A is positive, right? So now we can develop with obviously we are going to see how this model is developed, and what kind of growth are we talking about when we talk about the AK model. The idea is that we should have a constant rate of growth which would be positive in the long run, and how one would be able to achieve that, that's something that we'll be looking into in the next lecture. Okay, so I'll be uploading the lecture notes, and later on, then if you have any query, you can send me an email, or you can ask me while we are having the live session. So if you have a question with today's lecture, you can ask me now. All right, so we'll pick up from here next week. So have a good weekend.